last lecture, we are computing the integral 0 to infinity sin x by x dx, and towards that we have defined that f of x is equal to 1 over sin just. So, this, as we know, this goes to 0. Therefore, what we get is that sin n plus 1 half of x by sin x by 2, this is equal to 1 by sin x by 2 minus 2 by x sin n plus 1 half of x plus sin n plus 1 half of x into 2 by x, right. And we would like to compute this. So, if we look at the integral 0 to pi, then this is sin n plus half x by x, this is equal to on this side, this is if I take this 0 to pi 1 by 2 factor, you can take that, this is sin n plus half x by sin x by 2 and plus 1 by 2 into 0 to pi f of x, and then this is sin n plus 1 half of 2x dx. As you can see that this value, what we know that what is the value of this, and this is going to give me, so this value is nothing but here. So, now 0 to pi, this is equal to pi by 2, because the entire from minus pi to pi it is 2 pi. So, 0 to pi, and now f is a Riemann integrable function, it is bounded at 0, because that is what we are killing the cancellation. So, therefore, this goes to 0 as n goes to infinity by Riemann-Lebesgue lemma. Thus, plus this, thus lim 0 to infinity sin x by x dx, this is equal to pi by 2, hence that is what we have proved. Okay. Now, we will see another application of this Parseval identity. This is namely, suppose now if we had given with if f 2 pi periodic and differentiable piece and in C1. Even I do not need C1, I can do with the f is C1 piecewise, not entirely, that is also okay for me. Nevertheless, now that means this is saying that f prime exists and this is also Riemann integrable, belongs to or 0 to 2 pi. So, now what can I say about the relationship between f and f prime? So, what it says is a very important inequality in analysis, which is called the Wirtinger inequality. So, let f is in C1 0 to 2 pi and integral of 0 to 2 pi f theta d theta, this is equal to 0, then 0 to 2 pi mod of f of t square dt, this is lesser equal to 0 to 2 pi mod of f prime t square dt. And equality holds if and only if f is equal to a sin t plus some b cos t. So, easily one can see that if f is equal to a sin t plus b cos t, then the equality occurs. But now, how to prove this inequality? So, now I start with 0 to 2 pi mod of f of t square dt. So, by Parseval identity, I know that this is equal to n from minus infinity to infinity mod of f hat of n square, which I can write this as f hat at 0 plus summation mod n greater or equal to 1 mod of f hat of n square. Okay. So, now f hat of 0 is 0. So, this is nothing but mod n greater or equal to 1 mod of f hat of n square, which is lesser equal to, as mod n is always greater or equal to 1. Therefore, this sum is going to be lesser equal to mod n greater or equal to 1 n times f hat of n square. Now, n times f hat of n is what? So, this is nothing but summation over mod n greater or equal to 1 mod of f prime hat at n square, because f prime hat at n is I n f hat of n. So, this is lesser equal to summation over n equal to minus infinity to infinity mod of f prime hat at n. I am just, I do not have any information about f hat at 0, but this is a non-negative quantity, I can add that, hence this is going to be equal to this is a factor of 1 by 2 pi, rather I would put it over here. So, this is 1 by 2 pi integral 0 to 2 pi mod of f prime of t square dt, and that is what is the Wittinger inequality is. And now let us try to see that if f is a sin t plus b cos t, then f prime is going to be nothing but minus of b sin t plus a cos t, and you can see that both they are same. Now, if f is in this form, then the equality occurs. Now, if equality occurs here, then we need to show that f is of this form. Okay, so, now let us look at closely the proof. In the proof, what we have done, this is the only place where the inequality is occurring. Now, if this is equal to this, then all my calculation everywhere in between steps will turn into equality. Therefore, here in this step, this inequality will be replaced by equality. If both sides are equal, then this is going to be equality. This suggests that what does it mean? So, this says that mod n greater or equal to 1 mod of f hat, if equality occurs, then square is equal to summation over mod n greater or equal to 1 mod of n times f hat of n square, because this is going to force this inequality to be equality if equality is occurring there. So, now as you can see that this term for mod n greater than 1, this is strictly mod of f hat of n square is strictly less than mod n f hat of n square. Therefore, this can happen only when mod n is equal to 1. This shows that actually f hat of n, this is equal to 0 for all mod n greater than 1, or rather you can say this is same thing as greater or equal to 2. Therefore, the Fourier series of f is nothing but f hat of minus of 1 e to the power minus of I x plus f hat at 0 plus f hat at 1 e to the power minus I x. So, this we know that it is given that f hat of 0 is equal to 0, because integral 0 to 2 pi f theta d theta is equal to 0. So, this is nothing but f hat of minus of 1 e to the power minus of I x plus f hat of 1 e to the power minus of I x. Just using the Euler identity, we will get that this is equal to f hat of minus of 1, this is cos x plus I sin x plus f hat of 1 cos x minus of I sin x. So, if you take your A to be f hat of I times f hat of minus of 1 minus I times f hat of 1, then that is your A. So, you can find A and B such that f is going to look like A equal to A sin x plus B cos x. Okay. So, now another important identity for Fourier series, the Parseval identity, is that if f and g belongs to Riemann integrable function of minus pi to pi or 0 to 2 pi, then inner product of f and g, this is going to be equal to summation over n varies over z f hat of n g hat n bar. This is going to be another form of the Parseval identity. In order to prove this, what we will do is that we need a following identity which is true for any inner product space. So, this is we can write that for norm of f plus g square. Here I am taking norm of f by definition is f inner product of f minus, so all these are plus I times f plus I g square minus f minus of I g square. This is equal to 4 f inner product of g. This is simple calculation. You start with norm of f plus g square, this is equal to f plus g, f plus g, and then you use the linearity of this will imply this is norm of f square, or rather just one more step I will write f f plus f g plus g f plus g g. This is equal to norm of f square plus f g plus g f plus norm of g square. Similarly, you expand this f minus g norm square, which is f minus g inner product of f minus g, and all this norm f plus I g is f plus I g inner product f plus I g, and you do the simple calculation by this, and everything will get cancelled. As you can see from there, if I am taking the subtracting this, then this f square and g square term will vanish. Now, if you go on like this, you are going to get that this you see here f minus g f minus. So, let me just write one thing for you, plus norm of g square, this will come. Now, this is minus of f comma g minus of g comma f, and if you compute it, then automatically what you will get, everything will get cancelled. So, you will arrive at this identity. No, you will arrive at this identity. So, once you have that, so therefore, you can write it f g, this is equal to 1 by 4 norm of f plus g square minus f minus of g square plus I times norm of f plus I g minus f minus of I g. So, once you have that, now you apply the Parseval identity that is with us, because we know the what is the value of norm of f square, that is summation over mod of f hat of n square, and if you just by putting the Parseval identity, we get with the simple complex algebraic calculation, you can get that this is nothing but n varies over z, f hat of n g hat of n bar. Okay. So, sometimes this formula is very useful, and let us see one application of this formula in the Wittinger inequality. So, now Wittinger inequality says that if f is C1 and integral of f vanishes, then L2 norm of f is dominated by the L2 norm of f prime. So, one can get that if f C1 and 0 to 2 pi f theta d theta, this is equal to 0, then Wittinger inequality gives that. Now, what happens if I have and I take any g belongs to C1? If any g belongs to C1, then zero to 2 pi f of theta g of theta bar d theta square, this is less or equal to integral 0 to 2 pi mod of f of theta square d theta into 0 to 2 pi mod of g prime of theta square d theta. As you can see, I mean, so it is if our g satisfy the condition integral over g is equal to 0, integral over 0 to 2 pi g theta d theta is equal to 0, then this is nothing but just an application of the Cauchy-Schwarz inequality. But here remember that we are not given with integral from 0 to 2 pi g theta d theta is equal to 0. So, this suggests that we need to look for a different approach to do this. So, what we can get is f inner product g. This side is nothing but f inner product g. So, now by our polarization identity, what we have proved that this is equal to 2 pi summation over n varies over z f hat of n g hat of n bar. Now, therefore, because if I am putting the inner product, so this is a bit of I have 2 pi times this. So, square which is now less or equal to summation over n varies over z, I can put the modulus inside the sum mod of g hat of n. So, here what we can do is this is square. Therefore, by applying the Cauchy-Schwarz inequality in this sum, what we get 1 by 2 is factor is gone, n varies over z mod of g hat of n square. So, now this is less or equal to, this is 0 to 2 pi mod of f of theta square d theta, and now this one, as you can see that here there is a catch over here. So, now if this I can write it as this sum, because f hat of 0 is 0, then this is n not equal to 0, n varies over z. So, here we can replace this actually by n not equal to 0, and then this is n not equal to 0. Now, this one is dominated by n g hat of n square n not equal to 0, and which is, now this is nothing but with certain into 0 to 2 pi, this 1 by 4 pi factor is there. So, 1 by 2 pi here, this is 1 by 2 pi by 1 by 2 pi mod of g prime of theta square d theta. That is what. So, it is a clever way of getting because we do not have any estimate over g prime. So, what we need to know, that I know that this g prime theta is nothing but by Parseval identity, its L2 norm is n g hat of n square. So, we work from the Fourier transform side by using the fact that f hat of 0 is equal to 0, because we do not have any information about g hat of 0. So, that is the reason why we are, if g hat of 0 is 0, then this problem is trivial. To accommodate that, what we are doing is that we are taking the f hat of 0 is equal to 0 and killing the n equal to 0 part, then we are dominating the rest of the, for rest of the n, g hat of n modulus of g hat of n by n times g hat of n mod, and then we are again dominating that by the little L 2, I mean summation over n from minus infinity to infinity. And this what this trick is very useful. Okay. So, once we have that, and now we are going to address the question that given. So, this is the question is important. So, let a n be a sequence such that summation over n mod of a n square is finite. So, the question what we are asking, is it necessarily true that there exists a f which is Riemann integrable such that f hat of n is equal to a n. So, we are going to address this question in our next lecture, and then we will proceed to find some pointwise convergence, and if possible some more application based on the Parseval identity. Thank you.